Hi there, I'm Mr. Manoj. This is my first IGCSE paper 62, May-June 2015 series. And in today's past paper, which I'm going to discuss with you, is the important information. What you must keep in mind that this paper is worth about 20% of your credit. Some students find this paper relatively much easier compared to paper 42, but then again it depends on how students look at the paper. Particularly there are some 2 or 3 very tricky questions which you have to look very carefully. So let's have a look. I hope you have a sample of this paper as we go along. So let's have a look at the first question. Now here the question talks about burning of ethanol. So ethanol is a fuel. We're going to burn ethanol and we're trying to figure out the amount of energy that is going to be produced. So ethanol is kept here, and as ethanol is burned, the heat is being transferred onto water, 20 centimeter cube of water there, and the objective is to find out how much energy this would give off. The first part of the question says complete the boxes to name the piece of apparatus. Well, if you look here, this, I'm sure you do recognize, this is thermometer there. This is thermometer. That's something that most students are very comfortable with. But this one, well, it's supposed to be called as stand. It has a popular name, clamp stand. Then this will be much better off. And then if you look at this question here, give 3 other measurements a student should have taken. Now, if you just pay attention to this part, that ethanol was burned for 1 minute and the temperature of water was then measured. It means the final temperature, this is final temperature, the final temperature of water was already measured. So which means what's missing for you is the initial temperature of water. Initial temperature. Why do we need initial temperature? Because we need to find out how much was the heat gained by water. So yeah, if I have the initial temperature and final temperature, I can find out. Then I also need to know how much fuel which I have burned. I need to know how much ethanol was here before and after the combustion, which means I need to find initial mass of ethanol. Initial mass of ethanol, that's before ethanol is burned. And then I also need to know the final mass, final mass of ethanol. So with the help of this information, I can figure out how much was the amount of alcohol we used. And now this C part says, if this experiment was repeated with 40 cm cube of water, what effect would this have on your results? Well, if you compare with the earlier situation, you had 20 cm cube of water, and now you're going to use 40 cm cube. It means there is more water. But then the question didn't talk about the heat. It means you have to assume that the amount of heat what we are expecting to come from ethanol will remain the same. So if it's going to be the same heat in double the quantity of water, do you think the temperature of water will rise twice as that, or maybe half of that? I hope you guessed it right. There will be less rise in temperature. In fact, it will be exactly half the change in temperature. So we could say half. We could say half, or we could say lower temperature change. So that's one effect that can happen. Or also, if you want to bring it equal to the amount of heat that was absorbed by this, that means you have to keep on heating for a much longer time. So it will take more time. So you could also say it will take more time. Okay. Now the question talks about, if you're going to use a copper can, how will that be beneficial for you? Now don't forget, copper is a metal, which means it's a much better conductor of heat, which means if you compare this with glass, boiling tubes is made of glass and they are not very good conductors of heat. It means if this container is made of copper, all the heat that it receives will go in water much better compared to the glass, which means the temperature change is going to be much higher now, or water is going to heat up more quickly. So you could say you're going to have higher, sorry, try that right once again. Okay, so we're going to have, if we're going to use a copper can, the temperature change will be higher. The temperature change will be higher, or I can say water will be heated. Water will be heated faster. Okay, so that's basically the first page. So let's have a look at the second question now. And this question talks about, this question is connected to topic 8 of your curriculum. This kind of salts which has the 0.6 H2 are basically called hydrated salts. This is called water of crystallization. And there are 3 steps mentioned. It talks about some amount 50 cm cube of an acid, and it talks about chromium 3 oxide was added to it, and when there's no more any other possibility of chromium 3 oxide that could be reacted with the acid, there was some kind of a separation being carried out, and then you have to boil the solution. Okay, so that's the 3 steps that was mentioned. And don't forget, your objective is to prepare chromium 3 nitrate, and you're starting off with chromium 3 oxide, so the acid must be the one who is supposed to give you the nitrate, and that's how you have to think. So hopefully with that information you could figure out the name of the acid who could give you a nitrate. And yeah, you guessed it right, this is nitric acid. This is nitric acid, HNO3, that's the formula there. B part says what would be used in step 1. Well, if you're going to add solid chromium oxide, there is a special apparatus used in the chemistry labs for it. And no, the answer is not spoon. I don't know, so many children love to put that word. We call it spatula. That's the spatula. You should look this up in Google image and just type in the word spatula, see what it looks like. At least you have a fair idea. And how would you stir the mixture? Well, if you want to stir the mixture, the best thing to do is use glass rod. And the reason why we take glass rod is because it does not interfere with well, almost all the reactions that you do in your chemistry labs. Now the question says name the separation method used in step 2. You must understand, when they said no more chromium oxide was added, which that means, how would you know that no more chromium oxide could be added? That's when you start seeing some unreacted chromium 3 oxide, which would be in solid state, which means to remove a solid from a liquid, you'd carry out a process called filtration. So that's the answer there. That's the best answer. Filtration there. Filtration. Okay, there's also another process called decantation what can be used. Look it up, but then filtration is much easier, alternative answers for you. Suggest what was left in the evaporating dish at the end of step 3. Well, if you look at step 3, they literally boil the solution strongly for 10 minutes. Now, if you keep doing that, obviously this is not how you will get a crystal, because objective is to get a crystal, so you end up losing all that H2O there. And if you get a salt without the H2O connected with it, you would get what is called as anhydrous version. So this is called a hydrated version there. This is the hydrated version. And the anhydrous version is the one without the H2O. So you end up getting anhydrous chromium 3 nitrate. So you get anhydrous chromium 3 nitrate. Always have a habit of writing that oxidation number in the bracket as it is mentioned in the question, because examiners always appreciate these kind of things. Okay, how should the student have changed the method in step 3 to obtain a more pure crystal? Okay, well, pure and dry crystal, if the word crystal is used, it means the whole process becomes different. You have to carry out what is called as crystallization route. It means you heat the solution more gently till a point of crystallization, and then you just cool the solution down, and then you get those crystals out, which you need to filter, and you press them between the folds of filter paper. That's basically what you have to do. We will heat the solution gently. We will heat the solution gently till point of crystallization. Point of crystallization. When we say point of crystallization, that's where the solution is ready to form the crystals. It's saturated enough where it could form the crystals on cooling. So but you won't see the crystals at that point of time. So you need to cool the solution down, and then you will see the crystals. So you basically then filter out the crystals, and once you filter out the crystals, you need to dry them. You need to dry them between the folds of filter paper, between folds of filter paper. So that's one way to dry the crystals out, or you could just even leave them to dry. Okay, so let's have a look at question number 3. Here the question says there are 3 bottles of liquid, and they have lost their labels, so it's your job to figure out who is who. So you have potassium hydroxide, which is KOH, is a base. So that's a good information to keep in mind. Octane, well, octane is a hydrocarbon. That's a fuel we have to use, and of course you know what water is. Outline test you would do to identify and distinguish the liquid in each bottle. Okay, so how do we figure out if potassium hydroxide is present? What test can you do? Well, keeping in mind that it's a base, you could just use any indicator. So I think I'm going to use red litmus. So you know what happens when I dip a red litmus paper into the solution. What I expect to see that it turns blue. So that's one easy way to figure this out. Of course, I also understand this is a base. It means the pH value of this should be more than 7, and it's a strong base actually. So it should be around 12, 13. So even if I find the pH, I could using a pH paper, I could get a high pH to confirm this. Okay, if you look at octane, being a fuel, which means if I try to bring a lighted splint close to it, it will probably catch fire. So what I'm going to do is bring a lighted splint close to the sample of octane. Obviously it has to be very less in amount, not too much, don't forget, it's dangerous. So when you bring a lighter splint, so we expect it to catch fire. It catches fire because being a fuel, that's that one good thing it does all the time. It catches fire. Okay. Of course, and there are some other chemical tests you could think of, and then this makes most easy sense to everyone. How about pure water? The important point is pure. That's what you must remember. You must probably study this in topic 11 notes, that if you measure the boiling point, so just check its boiling point, and if it's pure, it should boil exactly at 100 degrees. So it will boil at exactly 100 degrees. So that's how you figure this out. And if there was some kind of an impurity, you would have seen there was a difference in that number. Okay, so at question number 4. This is a big question. It's one of probably the biggest question in the entire exams. This question talks about hydrochloric acid reacting with a solution of sodium thiosulfate. These kind of experiments you would do very commonly in your AS lab sessions once you start AS program. These chemicals react together to form a precipitate, okay, so which makes the solution go cloudy. That's the information to be kept in mind. That's the diagram there. It gives you the amount of acid, it gives you the sodium thiosulfate there, and that's the volume of the conical flask, 250 cm cube. The printed sheet has some marks on it. Basically, you're trying to see the mark from the top, and eventually you will reach a stage where you can't see it anymore. Okay, in the first experiment, now this is important, you need to pay attention as to how each experiments are different. In the first experiment, there was 50 centimeter cube of thiosulfate, and there's a 10 cm cube of the acid being used, and time taken was measured for the words to disappear. Now, compare how the second experiment was different from the first one. The second one had 40 cm cube of the thiosulfate. Quickly go back. The first one had 50, the second one had 40. But the second one had 40 of the thiosulfate and 10 of water. Now don't forget, when you add water to something, you're actually diluting it. You're making it less concentrated. That's another point to be kept in mind. When you look at experiment number 3, they decreased the thiosulfate even more and increased the water. That means the concentration is further reduced. Experiment number 4, still going downhill, 30 of the thiosulfate and 20 of H2O. By now you must have clearly understood that what's happening is the concentration of thiosulfate is constantly being reduced. And finally, experiment number 5, 20 of thiosulfate with 30 of distilled water. Okay, so time for you to fill in this particular page. So I'm sure you can do that yourself. So we basically have, in the first experiment, there was 50 of the thiosulfate. There was 0 water there. And if you look at the time there, that's 45 seconds. And then you keep moving on. In the second one, we had 40 of thiosulfate, 10 of H2O. And as expected, it has taken more time because it's less concentrated now. In experiment number 3, we had 35 of thiosulfate and we have 15 of water. And as expected, the time is even shooting up a bit more. It's about 66 seconds now. In experiment number 4, we had 30 of thiosulfate, 20 of H2O. The time going up to now 78 seconds. And then finally we have 20 of thiosulfate with 30 of water, and it took us 140 seconds. I hope you are paying attention to the fact that we have to write the answer in seconds there. So keeping in mind that 1 minute is 60 seconds, you need to figure out how many minutes, and then that's how you get all these numbers there. Okay, plot the results on the grid and draw a smooth line graph. Please be careful when they say smooth line graph, absolutely no pencil, no scale, sorry, has to be used. It must be a freehand. Well, what we can do is perhaps you could, I'll wait for a while, why don't you try to plot the whole graph quickly, and then we can take the question from there. Hoping that you would actually might have drawn the graph. What I'll do is I'll just give you a rough sketch of what it will look like, just to give you an idea, so that we can I'm sorry, just make it a bit smaller there. So it's gonna look something like this. I'm just giving a rough idea of a sketch, how it's going to look like, something like that. And once you finish the plotting, you can just check with that. H1, this question says, from your graph, deduce the time for the printed words to disappear if experiment 2 was repeated using 25 of thiosulfate. Well, 25 means that's somewhere here. So basically what you do is you just you take a line from here all the way, you just stretch that line there, and wherever it kind of course you're going to use a scale. I'm sorry, I'm just doing a rough just to speed up, and then you should just draw a line towards this side, try to figure out at what value you get there. I think the correct answer was somewhere between 90 to 110. your answer should be between 90 to 110. Please make sure you do that. I'm apologizing for the rough sketch, but that's just to save some time. I hope you understood the idea though. Okay, so let's have a look at this next part of the question. This talks about what happens if you're going to use do the same experiment using a lower temperature, and label this curve as lower temperature. Well, at lower temperature you expect more time to be taken, so I have time on my y-axis there, so I need to show more time. That means the sketch is probably going to start somewhere up here. It's going to take more time, and then of course it'll have the same kind of gradient, okay, but that's you have to highlight the fact that it's going to take up more time. So the start has to be higher up, and it moves away from the y-axis. That's the important thing there. Okay, so that's the answer for that question. Let's have a look at the next question, which says, in which experiment was the rate of the reaction fastest? Well, for this, what do you think? I mean, if you go back to those numbers here, if you see the volume of thiosulfate is the highest here, and that's obviously the most concentrated, and the time taken was the least. So that's why this experiment number 1 would be the right choice here. So that's the answer there, experiment number 1. And explain why the rate of reaction was the greatest. Well, as we said, it's more concentrated. So what happens when there's more concentration? There's more particles in the same volume. So which means there is more collision, more frequent collision. So that's the main point there. So there is more concentration, which means more particles, there, and because there are more particles, there will be more collisions. Next question, it talks about a student did one of the experiments using 60 cm cube of thiosulfate. Why this wouldn't be appropriate? Well, for this one, if you just quickly go back on the previous page here, if you notice the total volume, 50 plus 0 is 50, 40 plus 10 is 50, 35 plus 15 is 50, 30 plus 20 is 50. The idea was the total volume was always kept 50, and that wouldn't be fair if you take the volume as 60 then. So that's why. So volume has been kept steady at 50, so it's not going to be a fair test. So it will not be a fair test. So that's the idea. It's something to make you understand that it's almost like if you have a classroom full of 10 or 15 students, and if every student gets a different examination paper with different total marks, it's going to be difficult for teacher to, as we say, test fairly everyone on the same platform. Okay, the part K, towards the end of the question, says what will be the effect if you're going to use a burette to measure the hydrochloric acid? Well, a burette is much more accurate compared to measuring cylinders, so it's more accurate. So if it's more accurate, so you expect your results to be much better. So the measurements will be much better. And then if you're going to use, but then although it's more accurate, but remember it will take more time. It will take more time for the reaction to happen, or it will take more time for the acid to be added. So that's the down part of it. But that's 2 marks, because so you have to write 2 different things there. 100 cm cube conical flask, which means this is a much smaller conical flask compared to what was used in the previous page. They used a 250, and now I'm going to use 100. 100 versus a 250. A 251 clearly is much bigger. Just quickly show you here. That was 250 there. That's much bigger conical flask there. But then if you're going to use 100 cm cube, the difference that you will notice is in the depth area here. A smaller flask, you will expect this liquid to be spread more. So what happens is the particles are in contact much more. So there'll be a much greater number of collisions. It'll be a faster reaction. So if you use a smaller flask, it's going to take less time. It'll take less time. The reason is due to more depth. Due to more depth, there is more collisions. Well, what's happening here is, just to make you understand, if something is small compared to something which is much bigger here, okay, so if the liquid was spread somewhere here in a 250 cm cube, and you're going to spread the same liquid in 100, you see, it has much greater depth compared to a bigger vessel. So the particle end up having much more contact. That's why there's no transition elements involved. So they dissolved it, and let's have a look at filtrate. I hope you understand filtrate is the one that comes through the filter paper. The solution was divided into two portions, and the first of them was tested with sodium hydroxide, and the mixture was heated and gas was tested. Well, since the question clearly said there is ammonium present, now if you look at your test sheet for cations and anions, which is in the syllabus, it clearly says if you're going to do this for ammonium, there's going to be ammonia gas which comes out, and ammonia gas has a pungent smell. So that's why you write here pungent. That's because ammonia gas comes out. So pungent smelling gas. Pungent smelling gas released. Pungent smelling gas released. And it was also tested with pH indicator paper. So obviously ammonia it's a basic in nature, so pH paper turns blue or purple. So the paper turns, you could say purple, you can also say blue. Okay. Now the question talks about the second portion. You added nitric acid and you added silver nitrate. Now that's a very, very important information. Silver nitrate, and you go back here and check, and you have iodide. So if you look at the test for halides, chloride, bromide, iodide, they're all tested with silver nitrate. So if it's iodide, you will get a yellow. You will get a yellow precipitate. A yellow precipitate. There you go. Remember, if it was chloride, you would have got a white precipitate. For bromide, you would have got a cream precipitate. Now, if you look at part D, it talks about the residue is the one which is on the filter paper, and you add acid onto it, and some effervescence happened. That's definitely CO2 gas coming out, confirmed by lime water. And dilute sulfuric acid was added, and there was some white precipitate which was also formed. Okay, so let's have a look at all this information. E part, what is the pH value of the gas given off in test B? Well, test B was here. This is the ammonia gas we are talking about. Ammonia is a weak base, so that's why the pH should be somewhere, I could say 8 or 9. Identify the gas given off in D. Clearly that was carbon dioxide there, and because that's the only gas who could do this, turning lime water milky. And then what conclusion can you draw about solid K? Well, let's have a look at the part G now, which says what are your conclusions about solid K. Now, keeping in mind that we have sulfuric acid which was used here, which gives off a lot of sulfate ions. So I'm going to get a lot of sulfate ions from there, and I'm getting a white precipitate here, which means I could guess the cations could be barium, because barium sulfate is white, or I could think of Bb2+, I could think of that. These are the two best answers. Of course, there are more than one answers available, but I would recommend if you just stick to these two. Electrolysis lesson of your notes. This is, I think, topic 5 of your curriculum. We have concentrated hydrochloric acid being electrolyzed. The circuit is given. We have hydrogen electrode. That's the information given there. Hydrogen is formed at cathode. Good to know. Cathode is negative. Good to know that. And you must remember anode is positive. And cathode, hydrogen is always produced at cathode. That's the only gas you get there. Okay, so which means this one has to be your cathode, which means this one has to be your anode. So if you just quickly have a look at the notes that you've studied in this lesson, if there is hydrogen at cathode, it means you should be getting chlorine at the anode, and you should always think something about the chlorine. It's pale yellow. Of course, it has a smell like a bleach. Okay, let's have a look at the questions. It says, name a suitable metal to use for the electrodes. Well, to use one of the best metals to be used for this kind of electrolysis is platinum. And I think that's the probably best answer available. And why does hydrogen form at the negative electrode? Now keep in mind, if the electrode is negative, that means the ion that is going to go there will be positive. So basically you could say because the hydrogen ions are positive. So that's the reason why the hydrogen ions, they move towards the cathode. That's the equation, just an equation. I'm just giving you, just to give you an idea what happens there. That two hydrogen ions, they gain the 2 electrons to form hydrogen. So that's the equation which happens. The next question says, give a test for this gas. Now, to test the presence of chlorine, you must keep in mind chlorine is acidic and it's also a bleach. So what we will do is we'll pass, test means what you're going to do. So we'll pass the gas over damp. It's important that it has to be damp. If the wetness is not there, the reaction doesn't happen. So we will pass the gas over damp litmus paper. And what we are going to see is that the paper gets bleached. Paper gets bleached. Well, the meaning of the word bleached means it kind of loses its color. The last question suggests why the volume of gas formed at the positive electrode is less. Now, what you see in the diagram here is chlorine is being formed at the anode. Now, you might remember last time we jumped into a swimming pool, a lot of chlorine smell was there. That gives an indication that chlorine is soluble in water, which means compared to hydrogen is absolutely insoluble. But chlorine is soluble, which means the chlorine gas that you will get here will not be exactly all the chlorine that you would expect. So the reason here is because chlorine is soluble. Chlorine is soluble in water. So there you go. Okay, so let's have a look at the last question in this exam. This is question number 7. It talks about 2 different acid solutions given, Tastyton and Slimton, and you're going to react this with potassium hydroxide, which is a base, and the objective of the question is to figure out which one do you think is more concentrated. Well, there are 2 approaches what you could think of. You could do a very simple approach by, you could do an acid plus metal reaction. You know, when acid and metal react, we get salt and hydrogen. So the one which is more concentrated should give off more hydrogen. And if you're going to measure the amount of hydrogen in a certain time, let's say in 1 minute, so in 1 minute, whoever gives more hydrogen should be more concentrated. Obviously, I must take the same quantity of the metal in both the reactions, and I must take the same volume and concentration and the same volume of the sample of both the acids. The second approach could be, you could do a titration. I could put a certain amount of acid, the first sample, Tastyton, in the flask and add a couple of drops of indicator. I can add potassium hydroxide from the burette till the indicator changes color, record the volume used, and repeat this with the other sample, and whoever needs more KOH from the burette will be more concentrated. So you have 2 different approaches there. So I'm just going to write the first approach, the easier one for you. So my first point could be I'm going to add, let's say, 2 50 cm cube of the first sample, which is tasty ton. To 50 cm cube of tasty ton, we'll add, I'm going to add, let's say, 5 grams of calcium crushed, because if it's not crushed, surface area can also interfere. And then that's the first point. And then collect. I'm going to collect the gas in a gas syringe. And record the volume collected in 1 minute. This could be variable, 1 minute, 2 minutes. We're going to repeat with the other sample, which is slim tin. We're going to repeat with slim tin and compare the volumes. Compare the volume. So obviously the one which is more concentrated will give off much more hydrogen compared to the other in the same time frame. So the acid sample who gives off more H2 is more concentrated. Okay, that's it. I hope you found the discussion useful. Hopefully I will be doing much more of these in time. As you see, it has a few selected components, certain selected questions which are a bit more tricky. The last question, which is the planning question, and the titration question, and the test sheet question. Apart from these three, the rest of the paper generally is quite straightforward. But yes, you do require a lot of practice, and hopefully I'll be able to put up more papers for your practice sessions. Okay, all the best. See you again.